Hello everyone, I'm Dr. Tejashwini N, Associate Professor. Welcome you all back to my YouTube channel Study with Tej. In previous video already we were discussing about checksum and the same thing continues here. I had explained with 4-bit the same thing if it is applied to 16-bit words, then it is internet checksum. So the message has been divided into 16-bit words. The value of the checksum word is initially initialized to 0. All the words including the checksum are added using one's complement addition, and the sum is complemented. Zeros are made as 1 and ones are made as 0. So that complement we take it and that actually becomes the checksum, and the checksum is sent with the data to the receiver. At the receiver end, the message in the checksum is received and the message is again divided into 16-bit words, and same addition shall happen here. Okay, once complement addition, and the sum whatever we get, that is been again complemented and it has been checked with new sum. Or uh, if the value is a 0, then the message is uncorrupted, error free, and it is accepted. If the new value, the checksum what we have found at the checker, if it is a non-zero value, then the message is corrupted, error, it has error, and hence it is rejected, discarded. So if the same thing is explained with the algorithm, initially the sum is 0. Yes, we had certain numbers, if you can recall, 7, 11, just a second. Yeah, we had 7, 11, then what we had 12, then 0, then 6. If you can recall, these were the numbers. Same, I'm just trying to explain you with 4-bit. The same thing, initially it is 0, 0 plus 7 becomes 7. Here, again, there are more number of words. Yes, there are more number of words. Then it takes 11, then 7 plus 11 becomes 18. More number of words. Yes, likewise, it keeps adding, and once it reaches 6 there are no more words, so no, yes, it doesn't have any words, no more words left. Then it comes here, then left sum, you will check whether it is a 0 or a non-zero. If it is a non-zero, then you will have to do one's complement addition, that is left sum plus right sum you have to do. This how you do with uh, the left sum and right sum. It is done in the different way. That is simple, you just pulled out and you added the same thing, but how to pull it out is the logic here. I have to tell you. So the same thing, I shall simply take some, instead of 32-bit sum I will simply take one 8-bit sum and try to explain how left sum and right sum is calculated. Okay, just a second. Okay, to start with, simply I'll take, suppose the sum already we have got is, let me give it as 1, 1, 1, 1. Okay, then let it be 0, 0, 1, 1. For example, after one's complement addition, this is what we have got. Then this is 8-bit, but now we only want it as 4-bit. Here they have explained in 32 and 16. For our ease, I am making it as 8-bit and 4-bit. Okay, so if this is 8-bit, I should make it as 4-bit. On that note, what happens here, I have to pull this. This is my left sum and this is my right sum. So I have to add these two, correct? So to add these two separately, I have to extract this, and separately I have to extract this. This is simply, you can't extract like that as we do it here. It has to happen in the system. So how it is done? Left sum, if you can see here, it can be found by shifting the sum 16 bits. So here it was, since it was 32 bits, 16 bits. Since here it is 8, 4 times we have to shift. So suppose if I shift it, this whole thing, if I shift it to the right, then what will be the thing? That is, this 1 is copied here, this 0 is copied here, this 0 is copied here. Okay, likewise all these things happen, and at the end 0 is added, this is discarded, this is added. Okay, one time. Likewise 4 times if it happens, all these 4 bits are discarded and all these 4 bits are shifted to this side, and all these 4 bits are become 0. So my result will be something like 0, 0, 0, 0, 1, 1, 1, 1. Okay, If you can see, haven't we extracted the left part of this? Correct, we have extracted. Now our job is to extract only this part, that is all these should become zero, only this part should be there. To do that, what is the logic? We are anding, not adding, it is and gate, anding the sum with this. For our example, we don't need this, this is for 32 bits. For our example, 0f will do the job. What is 0f? 0 in hexadecimal, 0 is 0 0 0 0, correct? F is 1 1 1 1, correct? With this we have to add that whole thing, that is 1 1 1 1 0 0 1 1. That is actual result, whatever we had got this sum. So okay, let me keep this. This is already gone, this is done, this is our left sum, this is done. Now we have to do the right sum. Anding we have to do, and not add, it is and. If we do and, then 1 and 1 is 1, 1 and 1 is 1, 1 with 0 is 0, 1 with 0 is 0, and anything you add with 0 is 0. So if you can see, this part is extracted. If you can see here, it is so neatly extracted, and this is all 0. So this is my R sum. Now I can do sum plus R sum. Okay, I'll do it here. So 0 0 0 0 1 1 1 1. This you have to add it with 0 0 0 0 0 0 1 1. This you have to add. Once you add 1 1 is 0, got carry. So 1 1 1 is 1 and 1. So this is 0 and 1, 0 and 1, 1, 0, 0, 0. So this is what we have got. Again, this is not 4 bits. Same kind of operation is applied to this as well. And we, after applying that, obviously this part, if we try to do in the same procedure, it becomes like this. You add it here, and 1 and 0 is 1, 1, 0, 0. This will be our final answer. This is what our checksum will be, correct? And whatever we do this complement of that will be our actual checksum. So complement will be 1100. So this is the actual procedure used. Hope you have understood. So likewise, till that gets into whatever the options we wanted, like here it is 16 bits. So till it becomes 16 bits. Suppose after doing it once, if you end up with 17 bit, again we do the same kind of operation, and we make sure that it is in 16 bits. Once it is been done, okay, then the left sum is 0, which simply means it is fitting within the 16 bits. Then you complement that sum, whatever you have got, and that is taken as checksum, and it is passed to the receiver. And the receiver end, as I said, the same kind of procedure shall happen there, and you check. If while checking, I mean, once you have calculated, if it is 0, then it is error free. If it is a non-zero number, it has error, it is corrupted, hence it is discarded. As simple as that. There are two variations, we'll discuss that. Before that, there is a problem here in checksum. So CRC is more strong compared to checksum. Checksum is not as capable or as a CRC in error checking. How means, if the value of one word is incremented by 1 and another value is incremented same amount by 1, decrement and increment. For an example, I'll show you. Okay, here anyway it's a pointer. So 7, what we had, 11, then 12, then we had what else, 0 6, correct? So I make this, there is an error, this became 8 and this became 10, rest all is same. So two errors are there, but still addition of this, that is 8 plus 10 is 18 plus 12 is 30 plus 0 is 30, and this is 36. And once complement addition will be again 6, complement of that is again 9, the same thing shall happen. So you cannot identify such errors, and that's the reason this is not as good as CRC. To overcome this, there are two variations for introduced, Fletcher and Adler. So how it works. If you can see here, one initially the left and the right, it is initially taken as 0, but here the addition is in a different way, so that this word by word, if it changes, we'll get to know which word was actually being changed. That's the reason it has been added. This r, whatever is calculated, is again used by l, and this kind of uh, calculation of the sum will make a difference to identify us which frame or which part of that, not frame, I would like to say a part of the messages which we divided into embeds, which embed actually had an error, we can identify it. The rest of the procedure is as same till it is more data, you keep adding. Okay, once you keep adding and the checksum is found out by this formula, and that is being sent with the message to the receiver, the same thing shall happen at the other end also, at the receiver end. And if the checksum, same thing, if the checksum is 0, then it is error free. If it is a non-zero value, then it has errors, and hence it is discarded. Here in this Fletcher, it is 8-bit and 16-bit, both are there, and both have same logic. Next, coming to Adler, just like Fletcher, only two things. To make it more efficient, we have initialized R to 1, but whereas here we have taken one prime number 655 to 1. The rest all the procedure remains same, and here also everything remains same. So 256, we are just changing this to the prime number, and procedure remains the same, and the checksum is sent. It is checked. If it is 0, error free. If it is non-zero, then it is discarded because it has error. Hope you all have understood. By this, oh, one more thing, by this procedure you can make out which particular m bit had an issue. Chances of detecting is more compared to the regular checksum. So this was introduced. Hope you have all understood. Thanks for watching. Have a good day.